will move from model-first tinkering to ecosystem leverage thinking. Once you internalize that shift, your prioritization lens won't go back. Welcome to AI on AI, where we unpack the next frontiers with a blend of deep tech and boardroom pragmatism. Today, it's the era of agentic organization and a new reasoning paradigm called asynchronous thinking, or AsyncThink, where an organizer agent uses fork and join actions to coordinate worker agents that run concurrently to solve complex problems faster and more reliably. Think of it like a multi-core CPU. The LLM is the processor, the agent pool is your cores, and the organization policy is the program that schedules work. Only now it's learned, adaptive, and optimized via reinforcement learning.
Thanks. Let's set the research lens. The learning to organize problem asks not just, can an LLM reason, but can it learn how to structure its own reasoning as a system, dynamically choosing when to decompose a task, which subqueries to launch, and when to synchronize, with the organizer-worker protocol providing fork-join primitives. What's novel here is training the LLM to emit these actions in text, then optimizing the structure itself via RL. So instead of handcrafting workflows, the model discovers effective query-specific organizations.
Mechanically, the protocol is simple but powerful. The organizer decodes tokens and can emit think, fork I, join I, or answer. A fork I creates a subquery and dispatches it to an available worker from an agent pool of size C, which itself is just the same LLM instance running a worker prompt. The worker returns content in a standardized return block, and at join I, the organizer pauses if needed, then appends the worker's result directly into its context and continues. Crucially, this subsumes classic paradigms. No forks equals sequential COT, repeated forks on the original query equals parallel thinking, and AsyncThink learns to toggle between them.
From a systems angle, the big levers are agent pool sizing, C, worker scheduling, and join synchronization. Latency is governed by the critical path, not total work, so excessive forking can paradoxically slow you down if join barriers sit waiting on a long tail. We also have infrastructure-level considerations like KV cache memory pressure per worker, GPU stream allocation, and token-level back pressure when the organizer stalls on a join, so deployment is as much queuing theory as it is LLM design.
On product flows, the benefits show up wherever users need multiple valid answers or evidence coverage, math proofs, Sudoku, planning variants, code refactors. AsyncThink will fan out, harvest intermediary insights, and merge them. The UX implication is you can visualize branches as they unfold, surface intermediate race, returns for transparency, and give users controls like cap forks to 2 or prioritize depth first, which lets different personas trade speed against thoroughness.
Strategically, this opens up new ROI vectors in domains like analytics planning, expanding hypotheses concurrently, customer support, parallel resolution paths, and operations, triage across incident classes, with the study reporting roughly 28% lower inference latency versus parallel thinking while boosting accuracy on math benchmarks. For business leaders, that's a double win: reduced time to answer and improved correctness, which usually compounds into higher throughput and better user trust.
Under the hood, training is two-stage. First, a cold start format SFT teaches the LLM the action syntax, fork, join, return, using synthetic traces. Second, reinforcement learning optimizes the organization policy itself with a composite reward, accuracy of final answers, a format compliance penalty to avoid invalid orchestration, and a thinking concurrency reward encouraging productive overlap. We use a group relative policy optimization variant, where organizer and worker tokens share an advantage signal, and we mask worker return spans in organizer loss to keep credit assignment clean. Let's dive into the latency metric. You all mentioned critical path latency as the right measure rather than raw token counts. Can we unpack how AsyncThink computes that?
Sure, think of the overall trajectory as a DAG, where fragments of organizer text are separated by join points. For each join I, you compute the max of two quantities: the organizer's own progress up to that point, and the worker path that started at the corresponding fork J plus its subquery time. A dynamic programming pass over fragments gives you the sequential depth T, which is a theoretical lower bound on wall clock latency. Then we define a concurrency ratio eta as the average number of active workers per step normalized by capacity, and reward the model for useful concurrency without letting it game the metric.
Practically, we instrument token steps, organizer fragment length fi, latency to emit fork tags inside fragment j, and the worker's subquery token count. The DP recurrence accumulates these to compute Li per fragment and T at the end. Using T rather than raw token totals avoids rewarding wasteful forking that increases total compute but doesn't shorten the longest chain. This is how they show a cleaner accuracy-latency frontier where AsyncThink beats parallel thinking with around 28% lower T.
I want to push back a bit. This concurrency metric can still be gamed. If workers emit trivial stubs quickly, eta looks high while real progress remains organizer limited. Also, generalization claims, from countdown to 4x4 Sudoku, are intriguing but modest. I'd caution against over-extrapolating to open-ended enterprise tasks until we see robustness under distribution shift, stronger baselines, and verifier-integrated merges. Otherwise, fork join becomes a choreography of confident fragments without guarantees.
That's fair. The paper anticipates reward hacking with a threshold tau on the concurrency reward and uses a format penalty for illegal forks joins. Ablations show removing the concurrency reward increases latency and lowers accuracy, and skipping format SFT collapses concurrency to trivial patterns, consistent eta near 1C. So both components matter. On generalization, zero shot to Sudoku is a signal that the organization policy transfers. Structuring work is a meta skill. But we agree broader evaluations with domain verifiers and larger agent pools are the next step.
Let's make the numbers tangible. What did we actually see across tasks?
On multi-solution countdown, strict, all-correct coverage hit about 89% for AsyncThink, compared with around 68.6% for sequential and 70.5% for parallel. On math, IM24 accuracy roughly 38.7% and AMC23 around 73.3% with critical path latency near 1.46K tokens, notably shorter than 2K length baselines that still underperformed. And the accuracy-latency frontier showed AsyncThink winning across multiple length caps. Shorter worker budgets like 512 tokens plus synchronization still beat long single trace reasoning. That's the system's intuition at play. Short, specialized bursts with disciplined merges outperform single sprawling thoughts. But you must watch the join overhead, because if your organizer needs to validate each branch with heavy cross-referencing, you transfer latency from generation to merge time. We've mitigated this with streaming joins, partial returns, timeouts per worker, and soft cancel of laggards to avoid blocking the critical path.
On the RL side, we stabilize training by sampling multiple trajectories per query, e.g. 8 to 32, using group relative baselines to reduce variance, and assigning the same advantage to organizer and workers within a trajectory. That shared signal encourages coherent division of labor. If a worker helps the final answer, both roles get credit. Without it, you see misalignment where organizers overfork, but workers don't produce helpful artifacts. From a user standpoint, the magic is adaptivity. Some prompts need step-by-step focus, no forks. Others benefit from divide and conquer. We can expose a thinking policy setting, depth first, breadth first, or auto, and we show branch timelines so users can audit the path. This becomes an explainability asset when stakeholders ask, how did the model arrive here?
Translating to business cases. In supply chain scenario planning, AsyncThink can fork into demand shocks, supplier risks, logistics constraints, then join to propose hedged plans. We've seen parallelized scenario development reduce cycle times by 20 to 30% over multiple quarters compared to monolithic planning. In customer support, one branch synthesizes known fixes, another tests dependency conflicts, a third drafts a customer-safe narrative, merging to a higher first contact resolution rate without increasing handle time.
There's also a claim of generalizing to unseen tasks. How much should leaders bank on that?
Cautiously, Sudoku generalization is encouraging but bounded. I'd want to see zero-shot performance on code repair, retrieval-augmented analysis, or legal reasoning with verifiable checks. My contrarian take, the real bottleneck isn't compute, it's join coherence. As branches grow, merge complexity can dominate, so concurrency winds taper off. Amdahl's law applies. Anyone treating forking as free will hit diminishing returns fast. That's a great point. There's a merge budget reality. One heuristic we use is marginal concurrency valuation. Only fork if expected reduction in critical path latency exceeds the projected merge cost. This can be taught with reward shaping or via an auxiliary merge cost predictor that conditions the organizer's fork probability.
And to de-risk merges, you can plug verifiers, math solvers, type checkers, constraint validators. The organizer can delegate verify lemma L as a subquery, join the verdict, and prune branches earlier, turning merges from opinionated synthesis into evidence-backed consolidation.
Let's talk training data and evaluation rigor. How did synthetic data and topology randomization help?
The SFT data was synthesized with a strong model to teach protocol syntax and a variety of structures. Without randomizing topologies, we saw the organizer lock into a couple of patterns, like fork all then join all, which limits exploration. Adding random structures increased plasticity, so RL could discover better policies. Ablations showed skipping SFT crushed accuracy and shrank concurrency to trivial levels. And removing the concurrency reward increased latency, so both steps are necessary.
We also masked the worker-returned content in the organizer loss and included only the join tag tokens. This avoids giving organizer undue credit for content it didn't generate and tightens gradient signals around coordination points. It's a small detail with outsized stability impact.
Deployment tip. Mirror this discipline at inference. Tag every fork join return, validate indices, and enforce agent pool capacity. Invalid sequences should be caught early with a format penalty and a recovery path, e.g. autocorrect duplicated fork IDs, else you risk deadlocks or unbounded buffers.
And this is where governance enters. Teams need auditable logs of every fork and join, who authored which subquery and how merges occurred. If a harmful decision emerges, accountability must trace back to organizer choices, not just the model. I'd recommend default-on transparency modes and policy constraints like no more than n concurrent forks for sensitive domains to mitigate runaway complexity.
In regulated settings, auditability is a feature. A compliance team can inspect the reasoning DAG and verify that mandated checks occurred as parallel subqueries. Beyond risk mitigation, this builds stakeholder trust. People accept model outputs more readily when they see the decision fabric, not just the final answer.
Let's get specific with 3 business examples. Then we'll circle back to scaling and ethics. First, supply chain planning.
In a global manufacturing program, AsyncThink decomposed into procurement volatility, transport capacity, and demand elasticity subqueries, running them concurrently and then joining on inventory and service level constraints, cut planning cycles by roughly a quarter. More interestingly, the merged outputs included 3 distinct hedged playbooks rather than a single brittle plan, which improved resilience across 2 shocks.
Second, incident response in IT ops.
In a network operations center, AsyncThink forks into hypothesis clusters, configuration drift, BGP flaps, DDoS fingerprints. Each worker synthesizes logs and checks. The organizer joins and ranks likely causes, emitting mitigations. We observed lower tail latency on high-severity incidents because the model didn't wait to rule out unlikely paths sequentially. Beware, though. Fork limits and timeouts are essential to avoid swamping log pipelines.
Third, analytics for growth teams. For product analytics, one worker queries cohort retention anomalies, another tests pricing elasticity, a third analyzes funnel drop-offs. Then the organizer merges insights into experiments. Instead of a single narrative, product managers get parallel evidence streams and can pick a next best experiment faster. The UX is a living decision tree you can expand or prune.
Let me add a technical deep dive on join synchronization. There's a blocking versus non-blocking choice. Blocking. Join halts the organizer until the worker finishes, guaranteeing order. Non-blocking join inserts a placeholder and allows the organizer to continue, backfilling when ready. The paper uses blocking semantics for correctness. But in production, we often stream partial returns and let the organizer annotate provisional conclusions with confidence to keep tokens flowing. Streaming helps, but increases cognitive load at merge. Your confidence calibration becomes critical. My non-obvious concern, KV cache bandwidth, not compute, often becomes the bottleneck when C grows. So even with great policies, your hardware pipeline can throttle concurrency. Leaders need to plan capacity around cache traffic, not just flops.
Totally KV sharing, paged attention, and elastic batching matter. I'd also look into pinning worker prompts in cache so fork startup is cheap and using GPU streams to isolate long-running workers from starving the organizer. Think amateurs talk strategy, professionals talk logistics.
For scaling C, we'll need curriculum RL. Start with C equals 2, gradually increase, and add auxiliary losses that predict merge cost, expected worker value, and conflict likelihood. Otherwise, credit assignment goes brittle. Too many forks, sparse rewards. A hierarchical RL variant where sub-organizers manage their own pools could help once recursion is allowed.
Exactly. Recursive agentic organization is a natural extension. A worker promoted to sub-organizer can decompose its sub-problem, making tree depth adaptive. But you must keep the protocol simple and verifiable. Text-only tags worked well because they reused the LLM I/O surface without special architectures. On ethics, 2 issues. First, synthetic SFT traces may encode biases in decomposition strategies, so measure not just accuracy but fairness in who or what gets forked. Second, concurrency amplifies resource use. Put quotas and sustainability budgets in place. Transparency and opt-out controls for users are vital when branches touch sensitive data.
Governance playbook for enterprises. Define maximum agent pool per use case. Set concurrency budgets per request. Log all fork join events for audit, and align SLAs to critical path latency rather than average token speed. Also adopt verifiers wherever possible. What gets measured gets optimized, and verifiers give you measurable targets.
And keep the UI humane. Show the tree, but don't overwhelm. Surface only the most impactful branches with evidence. Allow users to expand details on demand, and provide guardrails like fork only into these categories. That balances power with clarity. The paper mentions an accuracy-latency frontier. How should leaders interpret that trade-off?
Treat it like an efficient frontier in portfolio theory. For any latency budget, AsyncThink delivers higher accuracy than baselines. You can dial worker lengths up or down to hit a target T, and the model's learned organization fills in the most valuable structure within that budget. We saw roughly 28% latency reduction against parallel thinking while improving accuracy, so you're moving the curve outward, not just sliding along it.
Technically, that outward shift comes from synchronized, evidence-aware merges rather than majority vote aggregation at the end. Majority vote waits for the slowest branch and ignores cross-branch reuse. AsyncThink interleaves exploration and consolidation. I'd still like to see comparisons against parallel with verifier baselines, not just majority vote. Once you add verifiers, the gap may narrow. But even then, a learned organizer that launches verifier subqueries mid-flight could retain the edge.
Agreed. The framework is compatible with verifiers. The organizer can fork verification tasks and join them to prune or confirm. The reinforcement signal can incorporate verifier scores instead of pure final answer correctness. This is the RL with verifiable reward sweet spot.
Failure modes. What breaks and how do we guard against it?
Common issues: duplicated fork IDs, agent pool overflow, join on non-existent subqueries, or never answer. We mitigate with runtime validators, watchdog timers, and a safe fallback path to sequential reasoning if the protocol degrades. Also, cap worker lengths and abort stragglers. Never let a long tail dominate your critical path.
Training-wise, degenerate modes include fork everything or never fork. Format SFT prevents syntax drift, and the format penalty RFE makes illegal actions costly. The concurrency reward uses a threshold tau so the model can't inflate ETA cheaply, and group relative baselines reduce attraction to noisy long traces.
Don't forget human in the loop. Enable a human as organizer mode for high-stakes tasks where a person approves forks or injects task constraints. Conversely, human as worker can be a fork target for subjective judgments, with full traceability of who did what, when.
For rollout, start with low-stakes, high-volume tasks to harden the pipeline. Track 3 metrics: final answer accuracy, critical path latency, and format adherence rate. Once stability exceeds your thresholds, graduate to regulated domains with verifiers and human review.
Looking forward 12 to 18 months, what's the practical roadmap? Phase 1, internal tools with AsyncThink for planning and triage. Phase 2, expose branch transparency and fork controls in user-facing products. Phase 3, heterogeneous worker pools, domain-specialized models, and tool-augmented agents. Each step adds capability and governance features.
Infrastructure roadmap: KV-efficient inference, stream-aware joins, elastic agent pools, and unified logging for DAG traces. Invest early in observability. Without it, you're flying blind.
Learning roadmap: curriculum on agent pool size, auxiliary predictors for merge cost and branch utility, and verifier-augmented rewards. Experiment with hierarchical controllers for recursive structures.
Research roadmap: scaling laws for organization, how accuracy and latency evolve with larger pools and heterogeneous agents, and rigorous generalization studies across code, RAG, and symbolic tasks. Policy roadmap: standardize fork join trace formats, define disclosure norms for multi-branch reasoning, and set sustainability budgets for concurrency. Transparency shouldn't be optional.
A contrarian closing thought: everyone's chasing more forks. The winning systems will master smarter joins. Merge quality determines ceiling performance. Invest there first.
One more measurement tip: always report both token level T and wall clock under real engines. Caching, batching, and interconnects change the story. Optimize for the system you actually run.
Heuristic for practitioners: fork where uncertainty is high and subproblems are loosely coupled. Join when evidence converges or contradictions appear. Don't let branches drift without reconciliation.
Strategy heuristic: deploy where latency and correctness compound value. Planning, triage, analytics. Then scale to domains where transparency is a regulatory asset.
Product heuristic: make the organization visible but optional. Power users will dive into branches, others just want the best answer. Meet both.
Ops heuristic: budget your joins. If merge cost grows faster than branch utility, cap forks and pivot to depth.
Ethics heuristic: no invisible orchestras, record the score, you can't govern what you cannot see. Scientific heuristic: make the implicit explicit. Once reasoning structure is a first-class action space, we can measure, optimize, and improve it.
And with that, we'll close. AsyncThink reframes LLMs as organizations that learn how to organize, blending algorithmic rigor with operational pragmatism. To our business and technology leaders, measure the critical path, make merges smarter, and treat fork policies as a strategic asset. Thanks to our panel, and thanks to you for listening. Before we say goodbye, let's stitch the full arc together. AsyncThink reframes LLMs as learned organizations. An organizer emits fork join actions to coordinate workers. A two-stage training pipeline, format SFT for syntax, RL for policy, discovers when to decompose, how to parallelize, and how to merge, and performance is judged by final accuracy and critical path latency, not just raw tokens. And that's what underpins the 28% latency reduction alongside higher accuracy and a better accuracy latency frontier.
Technically, the innovations are clean and composable. A text-native organizer worker protocol, think, fork I, join I, answer, that subsumes sequential and parallel thinking, dynamic programming to compute critical path latency across join fragments, group relative policy optimization with shared advantages so organizer and workers learn coherent division of labor, a concurrency reward capped by a threshold tau to avoid gaming, and careful credit assignment, masking worker returns and organizer loss to stabilize coordination. Wrap it with verifier forks for math, code, or constraints, and you've got RL with verifiable rewards baked into the organization.
From the business lens, the highlights are pragmatic. Better accuracy and faster responses, about a quarter less latency than parallel thinking, translate into higher throughput and trust. We see immediate value in scenario planning, customer support triage, and analytics ideation, where concurrent exploration plus disciplined merges produce multiple vetted options quickly. Adoption playbook is simple. Pilot on low-risk, high-volume tasks, track accuracy, critical path latency, and format adherence, then graduate to regulated domains with verifiers, audit trails, and human-in-the-loop oversight.
For production, think logistics. Size agent pools based on KV cache capacity, not just flops. Stream joins where possible, set timeouts for laggards, and enforce hard caps on worker lengths. Implement runtime validators for fork join indices, and a safety fallback to sequential reasoning. Observe real wall clock, not just token T-batching, paging, and interconnects, shift the curve. And invest in unified DAG tracing so you can debug merges and measure where the critical path actually lives.
On governance, make the orchestra audible. Log every fork and join, expose branch rationale on demand, and let sensitive workflows cap forks or require human approval. Treat sustainability as a first-class constraint with concurrency budgets, and standardize trace serialization so compliance teams can audit the reasoning DAG. Transparency by default turns oversight from after-the-fact policing into proactive risk control.
Cautions and North Stars. Merge quality caps the upside. Amdahl's law applies, so prioritize smarter joins over more forks. Compare against strong baselines with verifier-led aggregation, not just majority voting. Watch KV bandwidth bottlenecks as C grows, and remember that generalization from puzzles is promising but not proof. Stress test on code repair, RAG-heavy analytics, and legal reasoning with verifiable checks.
For research, 3 thrusts. Scaling laws for organization, how accuracy and latency evolve with larger and heterogeneous pools. Recursive hierarchies where workers become sub-organizers under curriculum RL. And verifier-augmented rewards that teach the organizer to schedule checking and pruning mid-flight. The meta-insight is that structure itself becomes an action space you can learn. Once explicit, you can measure it, shape it, and improve it.
Final takeaways. AsyncThink's key innovations are a learned fork join protocol, RL that optimizes the organization, not just the answer, a principled latency metric that reflects actual concurrency, and a deployment posture that unites engineering discipline with governance. Leaders should pilot where correctness and latency compound value, make merges smarter with verifiers, and treat the reasoning DAG as an asset. After all, as Deming said, what gets measured gets improved. Thanks for joining AI on AI, and we'll see you next time where we turn organization into acceleration. If this sparked useful ideas, share the episode with one colleague who'd benefit. Your signal helps us go deeper next time.